Okay, today I plan to discuss a new topic about double integrals in Cartesian coordinates. Yeah. Before that, do you have any question regarding our previous lecture? Yes, anybody?
Previous lecture is maximum points at the
Yeah, maximum, minimum, extremum. Yes. Yeah. So yeah, I've uploaded also the lecture notes in the in the e-learning. Yeah. Yeah. Okay. Before discussing the double integral, let so see the let's recall how this idea of in, excuse me, this integration came about. It The idea of integration, came from the problem of finding the area under a curve. Yeah, area under a curve. Yeah. So, for example, we have a curve y equal to f of x. What is the area under the curve, the blue curve, over the interval a to b, x between a to b? Yeah. We know how to find the exact area of a rectangle, of a circle, parallelogram. Yeah. But given a curve y equal to f of x, how do you find the actual area under the curve? So one approach is by using this approximation approach. We use an estimate. First, we come up with an estimate of the area under the curve. This is what the ancient Greeks have used, historically. So, okay, so we partition the interval a to b using into sub-intervals here. Okay, we divide the interval a to b into sub-intervals. So this diagram shows the integral a to b is divided into n sub-intervals. Yeah? The first sub-interval is a to x1. The second sub-interval is x1 to x2, and so on until the end. Uh, um, and then let's say the kth interval is the interval xk minus 1 up to xk. So over each sub-interval, we construct a rectangular bar here. Yeah? We construct a rectangular bar over each sub-interval. And we know how to calculate the area of a rectangle, isn't it? So the sum of the areas of these rectangles give us an estimate of the actual area under the curve. So we start with an estimation process. So the area under the curve is approximately, see, this is an approximation symbol here. The area under the curve is the area of the sum of the rectangles here. What is the area of the first rectangle? It is the height. The height is f evaluated at x1 times the width, denoted here is delta x. So we assume there are partition using uniform width here. Yeah, all the rectangles here has uniform width delta x. So the sum of the first rectangle is the height times the width. So that is fx1 times delta x. The area of the second rectangle is the height at the point x2, which is fx2 times the width, which is delta x. And until the end, the last subinterval, this is the last rectangle here. Over the last subinterval, the height is f evaluated at xn, which is where b is xn, times the width, which is again delta x. So the sum can be written in terms of this summation notation here. So this gives us an estimate of the actual area under the curve. How to get better and better estimates? We use smaller and smaller partitions. We use but when delta x gets smaller and smaller, that means the number of partitions gets higher and higher. Okay, so here we have divided the interval a to b into n subintervals here. So to get better estimates, we use higher and higher values of n. Okay, we increase the number n. We use higher and higher values of n. But that would lead to a smaller and smaller values of delta x, right? And that gives a better and better estimate. So we define the area under the curve as the limit of this summation as n tends to infinity. And if the limit exists, then it is denoted by this integral sign here. All right. So this is the how I mean the origin of this idea of integral. It came from the problem of finding the area under a curve. Okay, and you have learned how to evaluate integrals. Yeah. Um, there are various techniques to evaluate a single integral which you have studied before. Okay, now let's move on to double integral. Yeah. One way to introduce the concept of double integral is by considering the problem of finding the volume under a surface. Okay, previously we considered the problem of finding the area under a curve. For double integral, we consider the problem of finding the volume under the surface z equal to fxy. So here is an illustration. Here we have z equal to fxy. And you have seen before that the graph of z equal to fxy is a surface, right, in a three-dimensional space. And suppose the domain is the D. Okay, suppose we have restricted the domain z equal to fxy over some region D. Okay, so and then what is the volume of the under the surface z equal to fxy over this domain D. Okay, so we come up with an estimate first. We try to come up with an estimate first. We partition the domain D into several sub-rectangles here. Okay. Remember, for area under the curve, we divide the interval A to B into sub-intervals. So here we divide the domain D into rectangles here. Yeah, sub-rectangles as shown here. And suppose this is let's focus on this sub-rectangle. Let's call it the ith rectangle. And suppose there are many points in this ith rectangle here. And suppose the rectangles here have uniform width and length, yeah? Delta x, delta y here. as shown here. Yeah. So let's choose a representative point in this rectangle. Let's call it xi and yi here. Okay. So this is the ith rectangle. Okay, and a, a representative point in this ith rectangle is xi yi. Okay. Yeah. Now over each subrectangle, we construct a rectangular bar here. Okay, as shown here in green. So this is a solid rectangular bar, a 3D rectangular bar here. And we know how to calculate the volume, right, of a rectangular bar. It is the what the area of base times its height. Okay, and the area of the base is delta x delta y, and the height is f evaluated at the representative point xi yi. So we assume the volume of the ith bar, 3D bar, as the height fxiyi times delta x delta y. Okay, so the sum of all the 3D rectangular bars will be an estimate of the sum of the volume under the surface. Okay, so so again we have a summation here. So this summation gives us an estimate of the volume under the surface. Okay, we partition the domain into n rectangular into we partition the domain D into sub-rectangles here. Sub-rectangles here. So suppose we have n sub-rectangles. So the sum of the volume of the rectangular bars give us an estimate of the volume under the surface. Now to get a better and better estimate, we use smaller and smaller partition. Yeah? But that means we need to use more and more rectangular partition, right? Yeah. So to get better and better estimate, we let n here. We increase the values. We use larger and larger values of n to get better and better estimates. So that when we use higher and higher values of delta n, the delta x and delta y tends to 0. Okay. So we define the actual volume under the surface as the limit of this sum here as n tends to infinity. And if the limit exists, it is denoted as this double integral. Yeah, double integral of fxy dx dy. The double integral is over the domain D. Okay, the two-dimensional domain D here. Of course, for this uh, for this to be considered as a volume, of course, we need F to be continuous and also F positive, right? F positive on the domain D. If we were to view this as the physical problem of calculating the volume under the surface. Yeah. Okay, so that's just a simple extension of the idea in the single integral from problem of finding area under a curve to double integral from the problem of finding the volume under the surface. Yeah. And as a special case, if z equal to fxy equal to 1, just a plane, right? A plane that horizontal plane that passes through z equal to 1, then the area of the domain D is equal to the double integral 1 dx dy, isn't it? Why? Let's Here is an illustration why that explains why. If z equal to fxy equal to 1, z equal to 1 is a horizontal surface, right? It's a plane. horizontal to the xy plane of height 1 unit above the domain D. So the volume of this object here is the area of this D. Okay, this the area of the base area times the height. So it is the volume of this three-dimensional object here is the area of D times the height, but the height is 1. So therefore, we have volume equal to the area of D. Yeah, yeah. So that's why when Z is equal to 1, the volume can also the calculation of the volume is equal to the calculation of the area of the domain D. Yeah. So finding the area of a domain D uh, can also use double integral approach, yeah, to calculate the area of a domain D. Okay, we will see some examples of that later. Okay, how do we evaluate double integrals? Yeah. So there are several cases. First, we look at the domain D, rectangular domain D. Yeah. So let's first consider the case where the domain D is a rectangular region here. Okay, so this is so z equal to fxy is a surface directly above the domain rectangular domain D here. Okay. So that means x is bounded as shown in this diagram. X is between A to B, and y is between C and D. Okay. Yeah, so that describes a rectangular domain D here. And also let's denote dA, d capital A, as dx dy or dy dx. So one technique of evaluating double integral fxy, a dA, is to first, it's a double integral. First we evaluate the integral with respect to y, holding x constant here. So the limit of integration here is the limits for y. So y is between C and D. Okay, in this diagram here, y is between C and D. Okay, so we evaluate the integral with respect to y first. Okay, holding x as a constant. And then we integrate the result with respect to x. And x is between A and B. Okay, so here we say we are using the order dy dx. This is we say that this is double integral using the order dy dx. Alternatively, we can also evaluate the double integral using the order dx dy. First, we evaluate the integral with respect to x, holding y constant here. So, and the limits of x is a and b. Okay, and then we integrate the result. So the result is a function of y, right? Because the result of this inner integral is a function of y. Then we integrate the result with respect to y. Okay, where y has limits c and d. So in this second approach, we say we are using the order dx dy. Okay, so to evaluate a double integral over a rectangular region D, we have two possibilities: to integrate using the order dy dx, or using the order dx dy here. And these are also called iterated integrals here. Okay, the technique that we have shown here is also known as the iterated integrals here. And these are some results related to double integrals. For the first result, if the function f xy, we can write it as a product of a function of x alone times a function of y alone we can write it as a product of two single integrals here. The integral with respect to x only times the integral with respect to y only. But this is only limited to rectangular domain D. Okay, this first result is limited to rectangular domain D only. We will see later non-rectangular domains shown below here. I will discuss how to evaluate double integrals for non-rectangular domain. Yeah. The second result is something similar that you have seen in calculus for single integral. The double integral of a constant k times a function f is equal to the constant k times the double integral of fxy. And the integral of a sum is a sum of integrals. That is the third result here. Something similar also to the single integrals. Yeah. Okay, let's see some examples of evaluations of uh, double integrals. First, we want to evaluate this double integral x squared y cubed dA, where the domain D is described uh, consists of all points x, y, where x is between 0 and 1, and y, say y between y and 3. Okay, yeah. So the region D is a rectangular region, right? One can see that the region D here, let's make a sketch of the region D. This on the xy plane. X is between 0 and 1. And y is between, say, minus 1 and 3. So I'm just making a sketch here. So this is the region D. Okay. So all points in the region D has point xy. Consists of all points xy, where y is x is between 0 and 1, and y is between minus 1 and 3 here. So this is a rectangular domain D. Okay, we have seen that we can calculate this integral using either the order dx dy or the order dy dx. Yeah. Okay, let's try the order dy dx. Okay. This is the order dy dx. So we want to integrate with respect to y first. So what is the limits of the inner integral? We have inner integral, outer integral. The integral of the inner integral has limits.
Some 3 to negative 1.
The lower limit is minus 1, right?
Yeah.
Okay. And the outer integral has limits
1 and 0.
0 and 1, right?
Yeah.
So we must align them correctly. Okay, we must align the limits of the integral correctly. If you want to, the inner integral is with respect to y, so we have to use, so the inner integral has limits for y. The outer integral is with respect to x, so the outer integral has limits for x. Okay, so you have to, the order is very important here. Okay, so what is the integral of x squared y cubed with respect to y? You want to regard x as a constant.
X squared y to the power of 4 over 4.
Mhm. X squared y to the power of 4 over 4. Yeah, that is correct. And the limits are for y, right? So the lower limit y is -1. The upper limit y is 3. Okay. So we simplify the expression in the bracket. First, we replace what I can pull out x squared over 4. Um, First, we replace y by 3. We have 3 to the power of 4 minus 1 to the power of 4. What is that equal to? I'm sorry, this is x squared over 4. Okay, that simplifies to what? 81 minus 1, which is 80, isn't it? 80. This is, the value here is 80. So we have 80 over 4, which is 20. Okay, so I can pull out 20 and see that now it reduces to a single integral, x squared dx. Okay, and what is the integral of x squared? Should be a piece of cake. X what?
X cube over 3.
Cube over 3. Okay, and this is to be evaluated at the limits 0 and 1. So we have 20 over 3 times 1 cube minus, which is 1, right? That is just 1, yeah. So it is equal to 20 over 3. Yeah. Okay. Let's try the order dx dy. We should get the same result. If we use now, if I now using the order dx dy. Okay. If we now try to evaluate the integral using the order x squared y cubed. Let me denote this as I. So here we have I equal to this double integral. So now we also have I. Okay, now we want to x squared y cubed using the order dx dy. So now the inner integral is with respect to x. What is the limit? So the inner integral should has limits for
0 to
x.
1.
Yeah, 0 to 1, and the outer integral should
Negative
has
1 to
limits
3.
-1
To 3.
until 3. Yeah. So again, you see the order is very important here. What is the integral of, what is the inner integral equal to? Remember, now we want to integrate with respect to x, holding y constant.
X
Should
cube
be
over 3
x cubed over
y
3,
power of 3.
y to the power of 3, yes. This has now limits is 0 and 1 dy. Okay, so we have the outer integral minus 1 to 3. I can pull out y cube over 3, then x cube, 1 cube minus 0 cube, so that is equal to 1. So now we have the integral of the single integral. Okay, I will write the constant 1 over 3 outside. So now it reduces to the single integral with respect to y. What is that? What is the integral of y cube?
Y to the power of 4 over 4.
Over 4, right. This is from minus 1. I'm sorry, the upper limit is 3 here. Yeah. Okay. So I leave it to you to show that the result is the same as in the previous approach. Yeah, it is equal to 20 over 3. Am I right? Okay. Is it possible? Do we have is it possible to evaluate this using another this yeah, using this approach here, shown here, number 1, method 1 here. We have method 1, method some results on double integrals here. Is it possible to use the first result here? If the integrand can be written as a product of x alone times a function of y alone, then we can also evaluate this double integral using this first result here. But this is limited for rectangular domain D only. So here we have a rectangular domain D, and look at the integrand. The integrand is x squared y cubed. So it is a product of a function of x alone times a function of y alone. So we have another approach for this example. The integral I can also be written as a product of a single integral with respect to x times a single integral with respect to y cubed. Yes? Yeah?
I'm sorry, that's not me.
Somebody is saying something. Yeah. Okay. So in this example, the integrand x squared y cubed, okay, can be viewed as a function of x alone, which is x squared, times a function of y alone, which is y cubed. So we can write this, the double integral, as a product of two single integrals, one with respect to x only, and the other with respect to y only. So there should be no problem for you to evaluate these two single integrals. The first integral is what? X cubed over 3. X is from 0 to 1. The second integral is y to the power of 4 over 4. And y is between minus 1 to 3. Okay? And I'll leave it to you again that the result is also the same as in the previous two approaches here. Okay, and remember, this is only for the case where D is rectangular and the integrand is a product of function of x times a product times a function of y. Yeah. Not all integrand has can be written in that form. Any question for this first example? Any question? Okay, then let's try another example. Evaluate, say, the integral, the double integral dA over x plus y with the domain D consisting of all points x, y, and suppose it is also a rectangular domain. Y is between 1 and 2. Okay, let me sketch the rectangular domain D. So x is between 0 and 1, and y is between 1 and 2. So this is the rectangular domain here. Yeah, this is the domain D here. Okay. Look at the integrand. It's 1 over x plus y, right? The integrand is 1 over x plus y. Now, is it possible to write this as a product of two functions as before?
No, sir.
No, huh? So the answer is no. Yeah, it's not possible here. So we cannot use the third approach that we have used in the previous example. Yeah. So so one way is we can evaluate this integral either using the order dx dy or dy dx. So let's use the order dx dy. Let's try this order. Dx dy. Yeah. So the inner integral has limits for x. X is between 0 and 1. And the outer integral has limits with respect to y. Y is between 1 and 2. Okay, what is this? Yeah. So let's evaluate the inner integral first. What is the integral of 1 over x plus y? Think y as a constant. Anybody? If I were to write this, what is the integral?
Ln x plus y.
ln x, right?
Oh, yeah.
Yeah, ln x. So this one should be the integral of 1 over x plus y with respect to x is ln, right? Ln x plus y. Remember, y is a constant here. So and y x is between 0 and 1. Yeah. So when x is equal to 1, we have ln 1 plus y. When x is equal to 0, we have ln y dy. Okay, so now it reduces to a single integral here. So you can think of this as you can write this as a difference of two integrals, 1 plus y dy minus the integral ln y dy here. Okay, remember what is the integral ln y dy? This can be evaluated using integration by parts actually. Yeah. This can be evaluated by using integration by parts, and the result is recall, let me use ln x. The result is x ln x minus x. Okay. Actually, I must write down a constant also because it's an indefinite integral here. Okay. Yeah. The integral of ln x is x ln x minus x. So using this, so for the first integral, it is let's do this one by one. Let me call the first integral here as I1, the second integral here as I2. Okay, so let's evaluate I1, the integral 1 to 2 ln 1 plus y dy. Okay, I cannot use that the integral ln x dx formula because it is not in that form. So let's use the substitution. Yeah, say u equal to 1 plus y. So we have ln u, and therefore du is equal to dy. And the limits also change, isn't it, when we use this substitution? When y equal to 1, u is equal to 2. When y equal to 2, u is equal to 3. Now we can apply this formula here. So it is equal to u ln u minus u. And u is between 2 and 3. So that simplifies to what? 3 ln 3 minus 3 minus 2 ln 2 minus 2. Okay. Can we simplify that further?
Doctor, may I ask
Mm.
something?
Yeah.
How can how is the boundary limits change like that? I don't
Oh.
really understand that.
You see, we have this substitution here, right?
Uh-huh.
So when y equal to 1, u is equal to 1 plus 1.
Oh,
Uh,
oh, that's it.
okay.
Okay. Thank you, Doctor.
So when y equal to 2, u is equal to 1 plus 2. All right?
All right. Thank you, Doctor.
Okay. Okay, let me write it down here also. What does it means? When y equal to 1 implies u equal to 2. When y equal to the upper limit 2, that means u equal to 3. Okay. Yeah. Yeah, it's good. Ask. I like students to ask questions. Because maybe others, some others also might be wondering why. Yeah.
Thank you, Dr.
Sure. Okay, let's simplify this. This is what? 3 ln 3 is the same as ln 3 using the laws of logarithm. 2 ln 2 is the same as ln 2 squared. We have minus 3 plus 2, which is minus 1, right? Yeah, minus 1. So ln 27 minus ln 4 minus 1. And this can also be written as ln 27 over 4 minus 1, right? Using the laws of logarithm here. So that's for the first integral I1. We have another integral to evaluate, the integral I2, which is the integral 1 to 2. So what happened here? 1 to 2. What is this thing down here? Delete. Y ln no lny, right? Second integral here is lny dy. So using that formula, the integral of ln x, so this is y lny minus y is to be evaluated at 1 and 2. Okay, so I leave it to you. Okay, to show that this is the same as 2 ln 2 minus 1. Okay, I leave it for you to show the details. So therefore, I is I1 minus I2. I is equal to I1 minus I2. So 2 ln 2 is the same as ln 4, right? ln 4, yeah. So we have ln I1 is 27, ln 27 over 4 minus 1. And I2 is ln 4 minus 1. So see that minus 1 cancel out, right? Minus 1 cancel out. So we have ln 27 over 4 minus ln 4, which is, if using the law of logarithm, is 27 over 4 divided by 4. So the final answer is ln 27 over 16. Okay. So that's another example. So here I have chosen the order dx dy. So use the
Doctor,
yeah.
no need to solve lah. The loan.
No, this is
Yes.
exact. No need to use your calculator.
Oh, okay.
This is the exact answer, ln. Right? You use your calculator, then you will get an decimal places kan. So you may leave your answer in this form. This is actually the exact answer here. So alternatively, you can also use the order previously I used the order dx dy. You can also use the order dy dx to get the same result. Okay, I will not do it here. You can try this on your own. Okay, it's already 11:51. Let's have a 10 minutes break. Alright, let's look at some more examples of evaluation double integral. Suppose want to evaluate this double integral y cosine of xy dA, where d here is it's again a rectangular region. Where x is between 0 and 1, y is between 0 and pi here. Okay. So one way to see whether to see here that D is a rectangular region, look at both the limits for x and y. They are both constants, right? The limits for x are constants. The limits for y here, they are also constants. So that is an indication that D is a rectangular region here. Now, there are two possibilities. One is using the order dx dy, and the other is using the order dy dx. If I use the order, let's look at the integral. Let's call this integral I. Let's first compare the two possibilities. One using the order dx dy, y cosine xy dx dy. So the inner limit is for x between 0 and 1. The outer limit is for y is between 0 and pi. Another possibility is using the order dy dx. Then we have I equal to y cosine xy dy dx. So the inner limit is for y, and the outer integral has limits for x between 0 and 1. Okay. What do you think? Which one is preferable here? The order dx dy or dy dx? Both are equal. Okay, both should give equal result, but sometimes one order gives is easier than the other one.
dx dy
The
is
xdy.
easier
Why?
because if we do the dy dx, we have to partial fraction the two integrals, two y's.
Yes. You see, the order is requires integration by parts. You know, the order dy dx requires integration by parts. Well, for the first order dx dy, don't need. We want to integrate with respect to x only, holding y constant. So it should be easier to evaluate the integral, the double integral I, using the order dx dy, right? Rather than using the other order dy dx. So it should be easier. Okay, it should be easier using the order dx dy than the order dy dx, because for the order dx dy we can integrate directly without uh, having to use the integration by parts. Okay, so sometimes this is what one need to do, before evaluating double integrals, is to consider which one gives which approach is better, yeah, or easier, yeah. So here it is now clear that the order dx dy is easier than the order dy dx. So what is the integral with respect to x? It's what is the integral of y cosine xy with respect to x? Think of y as a constant. Okay, think of y as a constant. Is it not sine xy over y, isn't it? We integrate cosine xy with respect to x, the result is sine xy over y, right?
Yes.
So, suppose I write this down, cosine alpha x. Suppose I write this integral. Then it is clear it is equal to sine alpha x over alpha, right? So now the role of alpha is y here. So here y is between x is between 0 to 1. But first notice that y cancel out. Yeah. So we have sine xy only now. So first we replace x by 1, so we will get sine y. And then when we replace x by 0, we get sine 0. So sine 0 is 0. So we have the integral of sine y only. What is that? What is the integral of sine y?
Negative
This
cos y.
is basic calculus, negative, yeah, negative cosine y. Okay. So first we replace, let me pull out the minus sign. So we have cosine pi minus cosine 0. What is cosine pi? Cosine 0
Negative
is
1.
1. Yeah, cosine pi is minus 1. Cosine 0 is 1. So we have minus 2 in the bracket. So it is equal to 2.
2.
Okay. So you can see how much easier it is to evaluate the double integral using the order dx dy. If you use the second approach with the order dy dx, requires integration by parts. Of course, it still can be done. Okay, you should get the same answer also, but a lot more difficult using the order dy dx than the order dx dy. Okay. Let's look at another example. Evaluate this double integral here, xy e to the power of e y squared dA with d equal to suppose this is written together with the limits 0 ln2 here. It is 0 1, and suppose the order is also given here, dx dy with d consisting of all points xy such that x is between 0 and L2 and y is between 0 and 1. So x and y here, they are both bounded by numbers, right? Bounded by numbers. Yeah. So that's an indication that D is a rectangular domain. Yeah. Okay, what do you think? Shall we just evaluate I using the given order dx dy, or should we evaluate it using the order dy dx? If we attempt to evaluate this integral using the given order dx dy, what is required? What technique is required? Integration by parts again, you see? You will need integration by parts. So, what if we change the order? Wouldn't that be easier, isn't it? Integration with respect to y first would be easier, isn't it? Because we can solve this using substitution. We can solve this integral with respect to y using substitution. If I let the substitution u equal to xy squared, then du dy is equal to 2xy dy, right? Du dy is 2xy. And we have yxy there. See? We have this. We have y dy there. Yeah, we have y dy. In fact, we have, okay. Therefore, xy dy is du over 2. Yeah. Therefore, this implies xy dy is equal to du over 2. Okay, it's easier. It is easier to evaluate this using the substitution. So the outer integral has limit 0 ln 2. The inner integral after substitution is u is just e to the u over 2. E to the u over 2 du dx here. Okay. What is u? What is the inner? What are the limits of the inner integral now? when what? When y equal to 0, we will get u equal to 0. When y equal to the upper limit 1, we will get u equal to x, right? U equal to x. So the inner integral has the limit 0 to x. What is the integral of EU over 2? Anybody?
EU over
Yeah.
EU to U.
It's the same. It's the same, right?
Oh,
It's the same. The integral of e to the u is e to the u, right? Remember?
yeah, sorry.
Calculus. The
Yeah.
integral of u to the x is e to the x also, right? Yeah. So u is between 0 to x. Yeah. Okay, when u is equal to x, we will get, I can pull out 1/2. So we have e to the x minus e to the power of 0 dx. E to the power of 0 is 1, right? It's 1. So now it reduces to an integral with respect to x only. So this should be not a problem. The integral of e to the x is e to the x. The integral of 1 is x. So x is between 0 up to ln2. So now we substitute. First we substitute x equal to ln2. And then we substitute x equal to 0. Right? And then simplify. ELN2 is the same as 2, isn't it? ELN2 is the same as 2. So we have 2 minus LN2, then minus 1. Yeah, so that is, so the final answer is half of 1 minus LN2. Okay? I hope you can see why this is equal to 2, because in general, we have E ln A is equal to A, right? E ln A is the same as A. Or E ln A is the same as A. So something you need to know all this, some basic facts, you know. You need to remember some of these basic facts. Any so okay. So even though in this question you are given the double integral of dx dy, but we are not forced to use this order dx dy. Okay, so after some considerations, it is found that the evaluation of this double integral using the order dy dx is a lot easier than using the original order dx dy, which requires integration by parts. Yeah. Any question for this example? Okay, so those are some examples of evaluations of double integrals over rectangular domain. Now, what happens if, let's consider a case where it is no longer rectangular domain here. So this is one situation where the region, the domain D is no longer a rectangular domain. In this case, x is between numbers a and b. However, y are bounded by functions. See, y is bounded below in this domain. Y is bounded below by a function g of x, and bounded above by a function h of x. So if this is the case, then we must integrate with respect to y first. Okay, there is no other option but to integrate. You are forced to integrate with respect to y first, and then integrate the result with respect to x. Yeah. In another situation, we may have a bounded D where y is bounded between numbers c and d, and x is bounded by functions of y. Okay, so in this illustration, x is bounded on the left by x equal to g of y. It is bounded on the right by a function x equal to h of y. So in this case, we must integrate with respect to x first, because x has limits as functions of y. Okay, then integrate the result with respect to y. In another situation, sometimes we have to split the integral here. We have a domain D consisting of two parts, a D1, a D2 here. Yeah. Sometimes we have to evaluate the double integral as a sum of two integrals, one over D1, one over the integral domain D2. Sometimes we may also have this situation here. Okay, let's look at some examples of evaluation of integrals whose domains are not rectangular. Evaluate this integral here, 3xy dA, where R is a domain consisting of all points xy, such that x is between 0 and 2, but y here is bounded between 0 and x squared. You see, x is bounded by numbers 0 and 2, but y are no longer bounded by numbers. It is bounded by 0 and a function of x squared. Okay, so in this case, we must integrate with respect to y first, right? We must integrate with respect to y, because y are bounded by functions of x. So this is how we should write the iterated integral. The inner integral is with respect to y, and the outer integral is with respect to x. So the inner integral has limits 0 up to x squared. The outer integral has limits 0 and 2. This is how we should evaluate this double integral. So we must integrate with respect to x first, y first. What is the integral of 3xy with respect to y?
3/2 xy squared.
3/2 xy
xy
squared. Yes, that is correct. Okay. So let's substitute the limits for y. I can pull out 3/2x, right? Think of 3/2x as a constant. So first y equal to x squared. So y squared becomes x to the power of 4. Then we substitute y equal to 0, and y squared is 0. So now it reduces to an integral with respect to x only. We can write down the constant 3/2 outside the integral. So we have x times x to the power of 4, which is x to the power of 5. And the integral of x to the power of 5 is x to the power of 6/6. So, so 3/2 times 1/6 is the same as 1/4. And we have 2 to the power of 6 minus 0. Which is 2 to the power of 4, which is 16, right? 16. So that's the answer. If you try, you can also make a sketch of the region R. See how it looks like. So we have a parabola y equal to x squared, right? Parabola y equal to x squared. This is y equal to x squared. So x is between 0 and 2. So this shaded region is the region R. This shaded region is the region R. And x equal to 2, y equal to 4. So you see here, in this region R, x is bounded between numbers 0 and 2, but y is bounded by functions. The x-axis and the parabolic curve y equal to x squared. Can we evaluate this using dx dy? This is using order dy dx, right? Okay, let's think for a moment. Is it possible to evaluate this using dx dy? Is it possible? Can we evaluate this using the order dx dy?
I think it's impossible, maybe. But possible, but maybe complicated, maybe.
Of course, we cannot write this in this form, right? We cannot write it. You cannot just simply write like this. Okay. Now, we know that y is between 0 and x squared, and x is between 0 and 2. So it is wrong to write the limits. If you want to evaluate the double integral using the order dx dy, it is wrong to write the limits in this way. Okay, this is wrong. Because the outer limit has a variable x. The outer integral has limits involving x. So you cannot write it in this way. Yeah. But if I want to write using to change the order of integration dx dy, we must find the limits in the right way. For example, this if I solve for this is x equal to 2, x equal to 2, this vertical line x equal to 2, but x is equal to what? X is equal to square root y here, right? If I solve for x, x is square root y. It should be plus or minus y, but x equal to minus y is on the other side of the y-axis. And y is between 0 up to 4. So the same region R can also be represented by different way. X is between square root y and 2. See? And y is between 0 and 4. Isn't it? The same region R can also be represented as all points xy, where x is bounded on the left by square root y and bounded on the right by 2, while y is bounded by the numbers 0 and 4. So it is possible to evaluate the double integral using the order dx dy, but using this new representation of R. Okay. So let's try evaluating this double integral using the order dy dx. The inner integral is with respect to y, and y is dy dx, or I'm sorry, dx dy, dx dy. The inner integral is with respect to x, where x has limits square root y and 2, and y has limit 0 to 4. Okay, let's try this. Now the integral of 3xy with respect to x is what? 3 over 2 x squared y, isn't it? Y, where x is from square root y up to 2. Yes. So we can pull out 3 over 2. Can pull out 3 over 2y. So first we substitute x equal to 2, we get 2 squared. Then we substitute x equal to square root y. We need the square there as well. So now it reduces to an integral of single integral with respect to y only. Let me pull out the constant 3 over 2. So here we have the integrand y times 4 minus y. Yeah. So let's multiply y into the bracket 4 minus y. So we get 4y minus y squared. Then we integrate with respect to y. The result is 2y squared minus 1/3 y cubed. Y between 0 up to 4. So if we substitute y equal to 4, So we get 2 times 16. And then 4 cube is what? 64, right? 64. And y is 0, it's 0. So what is this equal to? 2 times 16 is 32. For the bracket term, let's put everything over 3. We have 32 times 3 is 96, right? 96. So 3 cancel out. What is 96 minus 64? 32, right? 32. 32 over 2 is 16. So which is the same answer as we have obtained using the first approach, dy dx. Okay? So it is possible to evaluate this double integral using dx dy, but you have to change the limits. Okay, for the region R, you have to find the right find alternative representation for the region R. Any question?
Sir, why
Yeah.
is dA become dx dy or dy dx?
Why dA is dA is the same as dy dx, also dy. It's an area element, you know. It is an area element. I have written it here. Yeah. dA is an area element. Is either dx dy or dy dx. The A here stands for area element. The area element. Remember we have like delta x, delta y here. Okay. Delta x, delta y. So the area element is the product. Yeah. I can say delta A is equal to delta y times delta x. Yeah. But when we take the limit n tends to infinity, okay, dA delta A becomes dA. Similarly here, delta x becomes dx, delta y becomes dy. So sometimes the product here is also denoted as a delta. Where is it? Where has it gone? Yeah. Yes. It's also sometimes written as delta A. Yeah. So this is also sometimes written as dA. Because dx dy is multiplication is commutative, right? X times y is the same as y times x. Yeah. Okay.
I see. Understand, sir. Thank you.
So, can you
Yeah.
make sure that so the double integral that means to find volume?
Yes. But this one has nothing to do with volume. This is just for evaluation of integrals here. Okay.
Also, for now, the
What I'm
example
showing
before
here
here.
is not technique for evaluation. Yeah. All these examples are for evaluation of double integrals. I didn't connect all this with respect to volume.
Also,
Okay.
we haven't yet to go to the we can calculate volume, right?
No. Yeah, later on we will see some applications. One of them is finding volumes. Okay.
All right, thank you.
But for
Thank you,
now,
doctor.
let's learn how to evaluate double integrals. For now,
Yeah.
let's learn how to evaluate double integrals. Yeah. Just like the single integral also, right? The single integral, you know, even though I introduced it through finding area under curve, but But doesn't that's one applications, yeah. But sometimes we just evaluate integrals just for the sake of evaluation, nothing to do with areas, right? Yeah. So here I'm using the volume, the problem of finding as a to introduce the concept of double integrals. Okay, I'm considering the problem of finding the volume as to introduce how the problem leads to the concept of double integral. So later on we will see some applications of double integral. One of them is finding volumes. There are other applications as well. A moment of inertia, center of gravity. Okay, we will come back to the problem of evaluating volumes later on. But for now, let's learn how to evaluate double integrals. Yeah.
All right, Doctor.
Yeah. Okay, let's look at one example test problem here as our final example. Let's look at the sample test 2. Test 2, yeah. Evaluate the integral 0 to 2 x squared over 4, the integral x squared to 4 of the integral 4x over square root of 9 plus y squared dy dx by changing the order of the integration. Yeah. This is a sample test 2 problem. The given order is dy dx, but it is suggested here do not evaluate this order, this double integral by using the order dy dx. You are suggested to evaluate this double integral using the order dx dy. There is a reason, actually, to make the evaluation simpler. Okay. Because if you want to evaluate this integral with respect to y, yeah, dx it will be it involves square root 1 over square root 9 plus y squared. Yeah, yeah. What is the integral of 1 over square root of 9 plus y squared?
Something tangent, but I forgot the
Yeah, not
equation.
tangent. It's not tangent, not arctangent. You need to use some higher transcendental function, right? Yeah. So okay, let's follow the suggestion, the advice. Okay, but of course you cannot write as I mentioned before. Of course, you cannot write it in this way. When it says changing the order of integration, it doesn't mean that you need to write it in this way. The inner integral has limits 0 to 2, and the outer integral has limits x squared up to 4. Okay, this is not what it is saying. Okay, let's okay, but the integral shows that x is between, okay, the given double integral shows that what are the limits for x and y, that x is between 0 and 2, x between 0 and 2, and y is between x squared and 4. Y is between x squared and 4. Okay. So here you see the limits are not totally numbers. The limits for x are numbers, but however, the limits for the bounds for y are not totally numbers. Y is bounded on the left by x squared, by a function. So let's make a sketch of this domain. So x is between 0 up to 2. Y equal to x squared. It's a parabola, right? It's a parabola. And when x is equal to 2, y is equal to 4. Yeah. So this is where is the region? Where is the region? X is between 0 to 2. Y is greater than x squared. So it is this shaded region here. Because y is greater than x squared. Yeah. And less than 4. So the double integral is over this shaded region as shown here. Now this, okay, so y equal to x squared is equivalent to x equal to square root y, isn't it? And y is between 0 and 4. Yeah. So this shaded region D, if I call this shaded region D, D can also be written as y between 0 and 4, and x is between, what about x? Y, no, I'm sorry. X is bounded on the left by 0 and bounded on the right by square root y. Okay, square root y. Yeah. X is bounded on the left by 0, bounded on the right by the curve square root y. And y, so therefore, the double integral dy dx is equal to the double integral with the order dx dy, where x is between 0 up to square root y, and then y is from 0 to 4. Okay, this is what is required to evaluate the integral, the double integral, by changing the order of integration. So this is a lot easier. The integral of 4x is what? 2x squared, right? The integral of 4x is 2x squared. Yeah. The square root 9 plus y squared remain the same because we are treating y as a constant. Okay, then we do the substitution. Yeah, this won't take long actually. So when x is equal to square root y, we will get 2y, right? When x is square root y, x squared is y. Yeah. When x is 0, it is 0. So now you see, it reduces to a single integral with respect to y, which you can evaluate using substitution, isn't it? You can evaluate this using the substitution u equal to 9 plus y squared. Okay, I'm sure you know how to evaluate this. So it shows that eventually the answer is equal to 4. Okay, so that's the last example for our class today. Any question? So this is a sample test 2 question here. Oh, yes. Okay, let me now show you the QR code for the class attendance.